Okay. Let's do one more. Let's say let's do two more actually, I think. Let's do the limit as x goes to let's say 2. Let's do 2x cubed minus x squared plus 1 over, well, let's say x squared plus 5. Okay. So this is sort of a complicated function, a rational function. And as long as the bottom does not become 0, I can treat the top and bottom separately. I can use the quotient property to say, okay, well this is going to be a big fraction. I'm going to have the limit on top. Limit as x goes to 2 of 2x cubed minus x squared plus 1. And notice I'm using parentheses. If I don't write the parentheses, then that would mean, like if I didn't have that there, right? Then that would mean that I have the limit of 2x cubed, which is a number, and then separately I'm subtracting x squared and I'm adding 1. That the limit doesn't apply to the x squared unless I say it does. So I need the parentheses so that I'm saying what it applies to. Bottom limit x goes to 2 of x squared plus 5. Okay. So in the top, come down here. I'm going to break this apart the same way I did the other one. At some point, we'll use the rules implicitly. We won't explicitly write them out all the time. I'm going over just a little bit. Please don't leave just yet. Let me do something real quick. Basically, every day I like to take a quick screenshot of the participant list so I know who was here. Not that I'm taking attendance, but I like to have a record, just from so I have a record for my own purposes. So in the numerator, I'm going to break this into 3 limits, so I actually need a longer line. Okay, so this will be limit as x goes to 2 of 2x cubed minus the limit as x goes to 2 of x squared plus the limit as x goes to 2 of 1. Okay, on bottom, limit as x goes to 2 of x squared plus the limit as x goes to 2 of 5. Okay, so in the numerator, this 2 can move in front. That's the constant multiple property. In this one, I can move the limit. Let's do this, in fact. Let's do this. In this one, I can take the limit and move it inside inside the square, inside the exponent. So I can do this. I'm going to cut corners. Well, I shouldn't cut corners at all. I was going to cut corners a little bit, but let's just not do that. So this is 2 times the limit x goes to 2 of x cubed minus parentheses limit x goes to 2 of x squared. So I moved the limit inside the exponent. This guy, this is the limit of a number, so just plus 1. Right? On bottom, I'll do the same thing I did on the top with the exponent. I'll move the limit inside the exponent. So I get parentheses limit x goes to 2 of x squared plus 5. Okay. Here, I can do the same thing, but with moving the limit inside the exponent. Here, I can use the identity property for limits. The limit as x goes to 2 of x is 2. So this will be 2. Let's do this first. So 2 times the limit as x goes to 2 of x cubed minus 2 squared plus 1 over 2 squared plus 5. Okay. And then here, I can say, oh, well, the limit as x goes to 2 of x is 2, using that identity property. So this will be 2 times 2 cubed minus 4 plus 1, or 4 plus 5. Okay, and so in the numerator, I get, was that 16 minus 4 is 12 plus 1 is 13 over 9. There you go. So that's a lot of writing. And what we're going to find is that I really didn't have to do all this writing. Now, we'll be using the rules implicitly. We'll be thinking them. Oh, I need to apply this rule. I need to apply this rule. Oh, I can do this. Oh, I can plug this in. Ultimately, what we're going to end up doing, which we're just about out of time, so I'll briefly say, ultimately what we're going to end up doing is take the 2 and just plug it in for x. And if that gets us a number, then we're good. That's the result. If we get something like 0 divided by 0, oh, now we have to be more careful. We have to do something else. But for like a rational function or a polynomial, you just plug it in, and that works. If we have a limit like this, and obviously if I plug in 0 for x, we'll have division by 0 on bottom, right? So that's not going to get us a result. But what about the top? If we get something like, say, 5 over 0, that's handled one way. That means we have an asymptote. But if we get 0 over 0, that means that something else is going on. So if I were to plug in 0, then I would get the square root of 0 squared plus 9 minus 3 over 0 squared. And of course, 0 squared is 0, plus 9 is 9. Square root of that would be 3. So the top is 3 minus 3. So I get 0 over 0. That tells me that I have something going on because I got a indeterminate form. Basically, I have to use algebra here. So I'm going to say that I'll just rewrite the problem limit as x goes to 0. Square root of x squared plus 9 minus 3 over x squared. And looking at this, it might not be at all obvious what needs to happen. I would imagine that you're thinking, well, what are we going to do? Obviously, we can't cancel the 9 and the 3 somehow. We can't combine them, right? We can't do like 9 minus 3. One thing that some people would suggest is someone might say, oh, well, we'll just do square root of x squared and square root of 9. We'll get x plus 3. Awesome. That actually does not work. Let's make sure we're clear on why. And no one has actually asked, but some of you might have been thinking that we would do that. So I want to clarify why we won't. So let's do that in red up here. If I have something like this square root, let's say 4 squared plus 9, right? So supposing we use the number 4. So you could say, oh, well, that 9, that's really 3 squared, right? That's why I have a 9, because the way this problem works out, the 9 is the square of 3. That's why it works out this way. But if I were to say, oh, well, that means I have 4 plus 3, just find the square root of each part, right? Like that seems reasonable. But you're dealing with math, just because something seems reasonable doesn't mean it's going to be correct. Well, when you're dealing with lots of things, I suppose. If you actually combine the radicand, the interior of the square root, well, we'll have 16 plus 9, that's 25. So that's the square root of 25, which is 5. And of course, 4 plus 3 is 7. So, applying the root in this way is equivalent to saying 5 and 7 are the same amount, which clearly they're not. So we can't resolve the square root that way. It just doesn't work. It might look appealing because we have a variable. It's not obviously wrong. If you have numbers, then it's very easy to check. Yeah, that's totally not correct. It's not going to work. Okay. All right, so I'm going to multiply on top and bottom by the conjugate of the numerator. So the square root of x squared plus 9 plus 3. And on the bottom, square root of x squared plus 9 plus 3. Okay. And on top, we're going to FOIL. And on bottom, we won't. The bottom will leave factored. So this will become limit is x equals 0 of a really big fraction. So I'm not going to cut corners here because I want to make sure that this procedure is totally clear. We're going to reuse this kind of thing later as well in chapter 3. So I'll have the square root of x squared plus 9 times itself, which I could cut corners and just get the result faster, but I don't want to leave out any details and then leave anyone confused. So take the time to write out each step. Okay, and then we'll have outer. So the square root of x squared plus 9 times 3. And I'll write the 3 in front. So I'll have 3 times the square root of x squared plus 9. Plus 3 times the square root of x squared plus 9. Did not make my line long enough. Okay, and then inner. So negative 3 times the square root of x squared plus 9. Minus 3 the square root of x squared plus 9. And you might see right away what's going to happen in the next step. And then the two last components, negative 3 times 3 is negative 9. And again, on bottom, we're not going to distribute. I will leave it as is, and you'll see why in a minute. Okay. So, as you may have noticed, we can cancel those two. Okay, so this is the limit as x goes to 0 of x squared plus 9 minus 9. And then on bottom, we still have x squared times the square root of x squared plus 9 plus 3. Okay, so it might be fairly obvious that these 9's cancel. 9 minus 9 is 0. And then, and I'm going to write this as a separate step. Well, you know what? Let me back up. Let me back up and explain why. Some people will look at this and they'll say, oh, great, we can cancel as x squareds. But you can't. That doesn't work. The x squared in the denominator is a factor, so it is available for cancellation. But the x squared in the top is a term in the numerator. It's not a factor of the numerator. It's being added to other stuff. So it's not available for cancellation, so you cannot do those first. Now, it does happen that when we can't get rid of these 9's, well, now you can, because the x squared is by itself. It's like x squared times 1 on top. So to be as clear as possible, I'm going to rewrite it like that. And on the written homework or on a test, you really should do these two steps separately. Because if you just cross out those as well, like if you cross out the 9's and the x squareds, I don't know what happened first. Oops. I don't know what happened first. You're not telling me what happened first, and the order does matter. So do those steps separately. You should really be doing one step at a time. I will say though, let me caveat. It's okay to go from here to here in one step. I think that's fine. Because this is a lot of writing. Or in fact, maybe better is not to skip this step entirely, but kind of like how I made 9 here. I didn't write 3 squared. Here you don't have to write this twice. When you go to the foiling, you have the roots multiplied. This part here highlighted now can just be written as x squared plus 9. But maybe you should put these there to show that they're there and then cancel. Anyway, I'm not going to be overly strict on points. Like I might take off 1 point for being unclear. So just make sure that your work is as clear as possible. And if there's steps where the order matters, but make sure you're showing them one at a time. Anyway, so on top we have x squared, and I'll write times 1, even though I don't really need to, but that is what's going to be left over after I cancel. And on bottom, x squared times the square root of x squared plus 9 plus 3. Okay, so now I can cancel those, and I have left over. And notice also I'm writing limit every single time. That's essentially, you have to write limit every time. There are other ways to show your work where you do all the algebra first. Like, say, okay, we have a limit that we're given. I'm going to take just the function, ignore the limit temporarily, do all my algebra first, and get a simplified version. So I'm not writing limit at all from the beginning. And then at the end go, oh, actually, now I'm going to apply the limit. But once I start saying, oh, this is equal to the previous thing, I have to say limit every time now because I'm continuing the original limit, right? I can't, if I leave this limit off, then I'm basically, it's either you just forgot or you don't want to bother writing it, but it needs to be there. But again, I would only take off like 1 point for that kind of thing, for a notation thing. Okay, so this is 1 over square root x squared plus 9 plus 3. Okay, well, now there's no reason that I can't plug in 0 because on bottom, while there's still an x squared, it's got other stuff along with it, and I won't have division by 0. So if I plug in 0, and notice I'm not writing the limit here because now I'm using up the limit and I'm plugging in 0. Remember, I'm basically using the quotient property, the root property, the sum property, and the exponent property of limits in order to, I mean, I could write all those steps, but as I said before, we don't need to write each of those individuals. As long as I don't get division by 0, I'll just plug it in. So this will be the square root of 0 plus 9 plus 3. Okay. So 0 plus 9, that's 9. Square root of that is 3. So on bottom I have 3 plus 3, so I have 1 over 6.